Chapter 21, Problem 14. Fill in and answer the following. Part A. Peptide bonds in proteins are the result of blank reactions between blank. So peptide bonds is also known as amides. And an amide is when you take an amine and a carboxylic acid. So for example, let's say we take a 1-carbon amine and a 3-carbon carboxylic acid. So it's very similar to the reactions that we were doing with the esters. We take the OH off of the carboxylic acid and an H off of the amine. So what did we call that when we took off an H and an OH? Well, those were called condensation reactions. Let me change it to a darker color. So I'm going to write out this product. So we're going to get the water, and then we have the carbon with the nitrogen. He still has 1 hydrogen on him. And then we have the rest of the carboxylic acid. And then we have a new bond in between the nitrogen and the carbon double bonded up. So that bond right there is the one that they're referring to in the problem. So that is the peptide bond. But it's not just asking about just some arbitrary peptide bond. It's talking about proteins. So in nutrition, proteins get a lot of hype. But what makes up proteins? What are the building blocks? The building blocks are called amino acids. So if you look at the name, amino is because they have an amine, and acid because they have a carboxylic acid. So the general structure of an amino acid is you have an amine, a carbon, and then a carboxylic acid, a hydrogen, and some sort of side chain. Now, different species have different numbers of amino acids. In humans, there's 20 possible side chains. Some fungus have more than 20, which seems interesting because fungi are much simpler species. And then some other species have fewer. But for humans, we have 20 possible side chains. Okay, part B. What's the difference between the primary, secondary, and tertiary structure of a protein? So in essence, this is looking at the protein from different viewpoints. So primary is the most up close. You can look at it. And so we want to know that primary refers to the sequence of the amino acids So a protein can have hundreds of amino acids. There's simple ones. For example, insulin is a protein. And insulin, I believe, has around 30 amino acids. But then super complex ones like the proteins that make up your biceps would have thousands of amino acids. But who's first, who's second, who's third in the chain is going to be coded for in your DNA. So what that sequence is called the primary structure. So then there's the secondary. So it's kind of like we're now taking a little bit step back and looking at the protein from a further viewpoint. So secondary is how the backbone folds. So some possibilities is an alpha helix. So it coils up. And there's also what's called beta pleating. So this is something like this. And then there's also some random shapes that don't have any particular name. Now, what holds these in these two particular shapes is hydrogen bonding. Entropy says it shouldn't be organized like this because we know that high entropy is preferred. So it must be going against entropy due to some sort of force, and the force is specifically hydrogen bonding. So then the tertiary structure is now, again, we're taking a step back even further, and we're looking at the overall 3D shape of the protein. So different proteins are going to need different shapes. So proteins that serve functions, such as enzymes, they tend to be globular. So more spherical shaped. But proteins that are used for strength, like your biceps and hamstrings, they tend to be more stringy. So there's lots of possibilities, but ultimately your DNA codes for it so that it will create this shape. And therefore it will be able to serve its function. Now, what holds it together in these different shapes is intermolecular forces between the side chains. So we said before in part A that there was 20 possible side chains. So some of those side chains can do hydrogen bonding. Some of them can do dipole-dipole. Some of them can do ionic bonding. There's also straight up just LDF forces. It depends on the specific amino acid as to what type of force it has. Part C, how many possible tripeptides could result if you were to mix valine, leucine, and cysteine together? So these guys are names of amino acids. And tripeptide means that you only have 3 amino acids in the chain. Okay, so if we mix these together, we're not just taking 1 valine, 1 leucine, and 1 cysteine with teeny tiny tongs and throwing them into a beaker, but rather we're going to take a bunch of valines, a bunch of leucines, and a bunch of cysteines. So they don't know who should be next to each other because this is not being done inside of a cell. It's not being coded for by DNA. So it's just going to be random hookups. So one possibility is you could have 3 valines hook up. And then if that's the case, you could have 3 leucines. You could have 3 cysteines. So they pretty much don't know. But then, right, you can have mixtures. So we could have valine, valine, leucine. We could have valine, valine, cysteine. So I'm just going to put ... etc. There's got to be a faster way. Well, we pretty much know that this is like a statistical problem. And so we have 3 spaces that we have to fill. And we have 3 possible options that can go into each space. So this first space, right, could be valine, leucine, or cysteine. The second space could be valine, leucine, or cysteine. And the third place can be valine, leucine, or cysteine. So if we multiply those, that means there's going to be 27 possibilities. So you can imagine that's why I stopped, because I didn't want to have to bother to writing out 27 possibilities. But then there could be the question of how many possible if you can't have the same amino acid twice. So in other words, like these first 3 that I wrote out, I had 3 valines. So obviously I used valine more than once. So if you can't have any repeats, we still have 3 positions. So that first position, you have a 1 in 3 chance. So there's 3 amino acids that can go in there. But if you can't have a repeat, then there's only 2 possibilities for the second position and only 1 possibility for the third. And so now 3, 2, 1 is only 6 possible. So if repeats, there's 27 possibilities. If no repeats, there's 6 possibilities.